Okay, welcome back. So now we've got Arun talking about synchronized playback in GStreamer. If the opportunity arises to ask questions, could you indicate you wish to, and I'll bring the mic to you. That saves the speaker having to repeat your question for the AV recording and the streaming. So thanks for that. Over to you.
Yeah, cool, thanks. Right, hey everyone, I'm Arun Raghavan. I'm here from Bangalore, India. I work on Pulse Audio and GStreamer, so if you use Linux and your audio is broken, it's almost certainly not my fault. So today I'll be talking a little bit about synchronized network playback with GStreamer. So quick show of hands, who's familiar with GStreamer already? Okay, reasonably large number of people, but it's about half of you. So I'm going to just walk through a very quick introduction of GStreamer. What GStreamer is a multimedia framework. It's basically a library that you can use to build your application if it deals with audio or video or both. It is pipeline based, and I'll just walk through that in a second. And it is modular. So how GStreamer is written is that there is a plugin system. Plugins provide elements which provide small bits of functionality that you string together and build your application using that, right? So if you wanted to do, if you wanted to play back an MP3 file, what you might do is use the file source element, which will read data from the file system, provide that to an MP3 decoder element, which will wrap some MP3 decoding library, decode those MP3 frames, provide PCM data, which you might want to convert using the audio convert element into whatever format can be played on your system. So that might be Pulse Audio or ALSA on Linux, or on Windows you'd use whatever direct sound or wave out or whatever that is. We have support for iOS, Mac OS, Android as well, right? So the audio sync can be a platform dependent sync. So all of these elements put together with some additional bookkeeping is basically a pipeline, right? A slightly more complicated example that involves audio and video. So you might have audio and video in a Matroska file. So similar to before, you might have a file source that reads from the file system, gives that data to a demultiplexer element, which splits up the audio and video stream and deals with them separately. And like before, we have one part of the pipeline dealing with audio, decoding it and playing it back using a sync, another part of it decoding video and playing it back with a sync, right? And this is, again, the whole thing together is our GStreamer pipeline. And you can imagine now that constructing any sort of audio-video processing pipeline should be fairly simple if we have the elements that we need. So if you wanted to build something to capture audio and capture video, compress it and send it out over the internet to talk to somebody else over video call, that would also be possible with GStreamer. And multiple such applications are possible with GStreamer, right? So that's enough about GStreamer. What we're here to talk about today is synchronized network playback, right? And why would you want to do that? There are multiple different sorts of applications that you could conceive of. So one possible use is multi-room audio, like you might get with a Sonos or Google Home system, where you have one or more speakers in a room or in multiple rooms in your house, and you want to play a song on all of these speakers at the same time. Another application that finds use in various kinds of places, including art installations, advertising displays, all sorts of things, are video walls, where you might have multiple display units that you want to put together in an array and make one big screen of, right? So that's another place where you might have each of those displays connected to a separate computer. These things are connected together, and they're playing different parts of the same video all at the same time. Right. We also have cases where in cars and planes you might have different displays that are playing back the same audio and video stream, and these also need to be synchronized, right? And the idea with all of these is that you've got a single stream that you're playing at the same time, and you don't want these to be out of sync. You want them to be playing together. So I'm going to take a quick detour into how synchronization is done using GStreamer. This is not actually the core of this talk. If you want to dig into more details, there was a talk at LCA in 2016 by Sebastian that talks about the actual mechanism itself. But to briefly go through what is involved in this process, right? There are three aspects of that you need to deal with to have synchronized playback across the network. The first thing is having the media accessible to all your nodes, right? And this can be done in multiple ways. You could have, say, an HTTP server somewhere that's serving up the media to all your nodes. You could just have all the nodes somehow synchronize the files and have them available locally. Or you could use something like RTSP. You could use an RTSP server to make media available to all your nodes. So that's the first part. The second part is timing, and this is, in some sense, the most crucial piece of the problem, right? So if you remember the pipeline that we showed where you have audio and video playing, right? Even on a single system, we do need to synchronize audio and video. So if you're playing audio and video together, you want to make sure that it's synchronized so you have lip sync, and when somebody's saying something, it looks like they're actually saying it. How we manage this in a GStreamer pipeline running on a single machine is that the pipeline has the notion of a clock, right? This clock is what all rendering in the sinks is synchronized to. So usually what happens is you have buffers that are flowing from the file to the audio and video parts of the pipeline, and these buffers are time-stamped. So in the simplest case, you might imagine that the timestamps start from 0 and progress. Say if the first buffer is 100 milliseconds long, the first timestamp would be 0, and the second buffer would have a timestamp of 100 milliseconds, and so on and so forth. And when the buffer reaches the sink, the pipeline has some notion of playback started at time equals t. So at time equals t, I should render the first buffer, and then at time equals t plus 100 milliseconds, I should render the second buffer, and so on and so forth. So we synchronize at each of the sinks to the pipeline clock, and since all the sinks are playing to the same pipeline clock, we can make sure that playback is synchronized within the pipeline, right? Usually, if you're talking about local playback, the clock is provided by the audio device itself. So the audio is being rendered at whatever rate the audio device is playing out audio, and the video is also being rendered at the same rate as the audio device. So that's how we guarantee synchronization there. But what GStreamer allows you to do also, in addition to using the audio clock in your pipeline, is to provide a clock externally. So you can, the clock in GStreamer is just an abstraction. It can represent any time source. So GStreamer lets you just say, here's a time source, please render the audio and video synchronized to this time source, right? And now that time source could be the audio clock, as we said before. It could be the system clock, the system real-time clock. It could also be a network clock, right? And that is the mechanism that we use to synchronize multiple pipelines across different machines to the same clock. So we use a network clock that, and we have multiple implementations of network clocks. We have one based on NTP, one based on PTP. Both of these are network time protocols for clocks to synchronize. And you also have a GStreamer net clock, which is an NTP-like implementation that we have in GStreamer. Just to back up, I realize I didn't explain why we need to synchronize, but basically each machine that you have has a little clock crystal running in it, and no two crystals oscillate at the same rate. That means that each machine that you have in your network has a slightly different idea of how much time has elapsed in 1 second, or what 1 second means. So we need all these different machines to have one clock source that defines what the rate of time is, and have them all basically run their own pipelines against that clock, right? So that's basically the second part of that we need for network playback in a synchronized way. So there was media, there's timing, and finally there's some control information that we need to distribute to all the nodes. So one very obvious thing that we've already alluded to is if you're going to start playback, then you need to tell all the nodes that playback has started at this time so that they can start playback against that reference time, right? And because you have a shared clock, as long as all the nodes share that same clock, they have the same idea of what that time is. You might also want to share other control information such as I'm going to start playback now, or stop, or pause, or seek, or all these bits, right? So if you have these three pieces in place, you can set up a system where you have multiple nodes that are paying media at in a synchronized way, right? Now, if you dig into Sebastian's talk from 2016, this does require a fair amount of in-depth knowledge of GStreamer. So you need to understand some GStreamer concepts before you're able to write such a system, right? And we found ourselves writing this a few times and basically thought to ourselves, can we make this easier for users of GStreamer, right? So based on this, the GST Sync Server project was born, right? It's basically a library to allow you to write applications that need to do this sort of synchronized network playback, right? The things that it does not provide a way for you to share media across your nodes, right? The reason for this is that we found that there are enough different use cases that people have that would be difficult to write something that covers everything. And these things are fairly standard outside of what we would be able to provide. So providing an HTTP server that serves up a bunch of media is fairly simple, or providing a synchronization mechanism for the nodes to just say rsync or whatever media to their individual nodes is something that you would need to solve depending on your specific application. So that's not covered by this library. What we do take care of is the clock, the clock and timing related things for all your nodes. And we provide a way to send controls across the various nodes, right? As the name suggests, it's a client-server based architecture. So what you do is you run a little server that deals with telling all the nodes what to play and providing pause, play kind of controls. And then you have clients, which are the actual nodes that do any video display or playing back of audio. So the server part takes care of a few basic things. You provide a playlist, which is just a set of URIs that you want to play. As long as each of the nodes knows how to open that URI, you're good to go, right? There's a control mechanism, so you can, as I said before, do things like play or pause. You can provide transformations, right? And the reason you want to be able to do that is, for example, in the example we had with video walls, right? You might have, say, a 2x2 grid of displays that you want to treat as one large screen. You are streaming the same video file to each of these clients, but each client is going to apply a transformation to the video before rendering it. So in this 4x4 grid, the top left display will need to divide basically crop out the video divided by 4, play only the top left, then the top right display will show the top right of the video, and so forth. You might also want to do a bit of cropping to basically deal with the bezels on the display so that it looks like it's one big display and not just divided by 4. So you want to account for the bezels so that it looks continuous. right? And we have some mechanism to notify the server when a client joins or leaves, right? So API-wise, the idea is that it's supposed to be very simple. So you create a GST sync server object. This is all based on GObject, which is an object system for C that we use in GStreamer and other projects based around GNOME, right? So it's fairly straightforward. You create a new sync server object, you provide it a playlist, you start it, and that's pretty much it. And then there are some controls like setting it to paused and unpausing it, right? On the client side, it's even simpler. You basically need to just more or less point to a server address, and that's that, right? We do provide a way to sort of customize how you render audio or video, because especially on embedded platforms, you might want to say use say an accelerated video sync so that your display is smooth, or you might want to make some special controls to create a full screen window on the system that you're on. So Playback is basically a high level element that GStreamer provides that you can give a custom audio sync or video sync to. So if you want to control this, you can create a Playback element and provide it to the client, and it'll use that Playback to render the audio and the video, right? And the API is quite simple. You create a new client. When you're creating it, you point it to the server. Whatever address you provide will be used, and then you just start it, and it will automatically get information from the server and start rendering it, right? That's pretty much it. This somewhat ugly diagram kind of shows what's going on there. So you have a server. The server is it's a program, so it can be running on any of the nodes that's also running a client, right? And the client is running, so you're instantiating a GST sync server object on the server, a GST sync client object on each client, and there's this control plane that's taking care of all the messages and everything under the hood, right? Any questions so far? Anything that didn't make sense? Okay, cool. So let's keep going, and then maybe at the end, if there are questions, we can get to that. So this is pretty much all you need. If you just want to create an application that does synchronized playback, you basically just need to use the sync server and sync client objects, and that's pretty much it, right? But we found that not everybody, like people want more control sometimes over the actual way in which we send control messages out, right? The default that you saw where we have this control part and the network in between, we have a TCP server running on the server, and clients connect to that server and exchange information using a custom protocol. But there are applications that might want to implement their own transport for these control messages. So for that, we basically allow you to override the control interface by providing a control server and a control client, an implementation of a control server and a control client interface, right? So if you're implementing a control server of your own, you basically you need to provide some way to say, hey, listen on this address, assuming it's TCP based or UDP based. You need to provide some way to synchronize a sync info object. So it's a well-defined object. You need a way to serialize and send this out over the network, right? It's some controls for starting and stopping, and you need to provide a mechanism to notify the user of this interface that clients have joined or left, right? If you're implementing the client side, again, you need to provide a way to say, hey, this is the address of the control server that you provided. This is a way to deserialize that sync information that needs to be provided to the GST sync client, and a way to start and stop, and a way to identify the client, right? And the reason we want to have this kind of identification and configuration for clients is so that you can have, the server can dynamically adjust what it's doing based on the clients that joined, right? So if you have a video wall, maybe you can configure what the transformations are based on whether there are 4 clients or 9 clients or 16 clients, and that would allow you to determine the size of the screen. Or in a multi-room audio setup, if you have just one speaker, you want to play everything to it. But if you have two speakers and you know one of them is the left and right channel, you might want to treat it as a stereo pair and play left to one and right to another, right? So this mechanism is meant to allow you to do that, right? And that's pretty much it. I realize I'm almost done now. So if you want to make a simple application, there's a GST sync server and a sync client object. If you want to have control over how messages are sent back and forth, you have that. We need to still merge this into the GStreamer repository. This has been pending me finding the time as well as getting some feedback on the API. We need to provide more controls and more examples. And there are some things within GStreamer that we can do to get tighter sync. It's fairly decent right now, but we can probably do better. And yeah, that's it. There's a little demo with that very shaky video. The video on the left is running off my laptop. The one on the right is running, I believe, off an Odroid board. And you'll see that when they start, there'll be the video on the left will start before the video on the right, but they'll be in sync soon after. It's playing Tears of Steel, the Open Blender Foundation video, which will start soon. Yeah, that's it. Thank you for listening.